Hello. Today's lecture is going to be on the common but fascinating and complex process called spontaneous imbibition. Now, what is spontaneous imbibition? It's where a wetting phase displaces a non-wetting phase in a porous medium, and it's spontaneous because there's no driving force. You're not injecting, you're not pushing the wetting phase in. The only force that causes the wetting phase to go into the porous medium is capillary pressure. So you see it in lots of different examples. How do plants take up water in their roots? What happens if you spill something and you soak it up with a tissue? Yes, that's a spontaneous imbibition process. So just let's see it. Here's some water. We have a tissue which is a fibrous porous medium full of air. Okay, so the spontaneous imbibition process is where water displaces air. Now, what I'm going to do is I dip the tissue in there, but what you notice, okay, is the tissue gets wet. It gets wet above where I put the water in. The water has moved up into the tissue. It's done so because capillary forces, the capillary pressure, wants the water to move into the tissue. It's competing against gravitational forces, and so eventually you reach some equilibrium. Let's take another process. We're interested in rocks. Okay, so here I have a sandstone. It's a dry sandstone. It has a sort of quartz surface. Okay, so what happens if I dunk that in the water? Okay, so here we have the water here. I'm going to put, again, try and get it so you can see. Okay, so I dip it in here. Now, what are you seeing coming off the top here? Okay, can you see all the bubbles of air? So the water is surrounding this rock, okay, imbibing into the pore space. I'm not injecting it. I'm forcing out the air with these bubbles. And we can see the bubbles, okay, continue to imbibe. Here, the imbibition process is taking a few tens of seconds to complete. Okay, now we have a wet piece of rock. There will still be some air in here, still full of bubbles. Okay, there'll still be some trapped air. Okay, but the rock has now imbibed a significant amount of water. So how can we now describe this mathematically? I've got the blackboard. I'm going to write equations on the blackboard. So let's describe it first physically, and then the mathematical model that we're going to use. So what we're going to do mathematically is describe the process in one dimension, one-dimensional incompressible flow. Wetting phase goes in, a non-wetting phase comes out. So the way in which we can describe it, as you can imagine a rock like this, this will be the x direction, this will be the location x equals 0 here. Then we'll have a wetting phase that will imbibe into the rock. And because it's a one-dimensional flow, we're going to assume actually that all of these surfaces are blocked. So the only way in which the non-wetting phase, say oil or air, can escape is actually through the inlet. Okay, so this will be, just for the sake of argument, if it was oil and water, right? If we're looking at oil recovery, right? This will be water and this will be oil. So we see this type of process in fractured reservoirs where water can be injected through a fracture network, surrounds, quotes the matrix, the normal rock. The only way in which the oil in that matrix can be recovered is by water imbibing and oil escaping. Okay, well, now needs to specify some initial and boundary conditions. Okay, so what we're going to specify here is initially at time t equals 0, the saturation is going to be some initial or connate value. And we'll assume that this initial saturation is immobile. Okay. Then what are the boundary conditions here? Water goes in, oil comes out. Here we may have a fracture or the open air, as I showed in my examples. So what's the boundary condition? The boundary condition is there's no capillary pressure. The capillary pressure here, PC, is 0. Now, what does that mean in terms of saturation here, where the capillary pressure is almost 0? So let's draw a capillary pressure curve. Okay. PC against SW. Now, if we looking at water flooding, because the water saturation is increasing, it's an imbibition process, okay? This will be 0. This is our connate water saturation. A strongly water-wet rock would show something like this. This is 1 minus SOR. So when PC is 0, we're at 1 minus SOR. But that's not the case if we're looking at rocks for all circumstances, is it? Imagine we have a mixed wet rock. If it's mixed wet, we tend to have a capillary pressure that looks like this. It has both a positive piece where the water imbibes through the water wet regions of the pore space, and another region where the water has to be pushed. That's not spontaneous. So if we have a mixed wet rock, the saturation where PC equals 0 is not 1 minus SOR. You don't have a residual saturation at that point. Okay, it is what it is. Okay, so let's define this saturation S star. Okay, and that's defined such that PC of S star, we can put a W here if we like, is 0. Okay, so the capillary pressure at S star is 0. So this is the boundary condition, is that SW at x equals 0, okay, is SW star. Okay, so that's set up the problem. Okay, we got the capillary pressures, we have this boundary condition. Eventually, when the imbibition process is completed, the saturation will be SW star everywhere, but initially it's SWC. So the saturation varies from this value, not all the way to the residual saturation, okay, but to the SW star here. Okay. Now what we're going to do is describe it mathematically. Okay. So we need a little bit more space here on the board, and in fact what I'm going to do is remove everything here so that I get a little bit of room for the mathematical development. Okay, so let's write down the conservation equations, and we've met the conservation equations actually in previous videos. Okay, so the first equation we're going to write is the conservation equation for water in one dimension. Okay, now we've met this before. I've written it here in terms of the water Darcy velocity. So it's the volume of water flowing per unit area, per unit time. I'm not introducing the fractional flow, I'm not doing anything else. This is what's been derived before. Okay, now we're going to write down what QW is. And this, again, we've done before in general for two-phase flow porous media. QW has 3 terms. It has a term which is proportional to the total velocity, okay? And that's sort of going with the flow, that's the effective term. We have a second term which is due to gravity, okay? And we have a third term which is due to capillary pressure. Now this term, okay, if I go around here, this term here, this final term here is a capillary pressure gradient, and this can be written as dpc ds ds dx. Okay, so it can be written like this. Now, when we're looking at spontaneous imbibition, the particular example we're going to look at is strictly called countercurrent, where the water moves in and the oil moves out in an equal and opposite direction. So strictly speaking, this is countercurrent spontaneous imbibition. Countercurrent, okay? It's countercurrent, which means that for every cubic meter of water moving in, a cubic meter of water, of oil has to move out because it's incompressible flow. So this means that QT is 0. Okay, so if QT is 0, this term disappears. I'm not going to go through this in much detail, but the gravitational force, when we're looking at most of these examples, is relatively insignificant. So for instance, in the piece of rock I showed, the effects of gravity is minimal. Maybe it's significant in the tissue paper, but I'm not really analyzing tissue paper, I'm analyzing rocks. When we're looking at fractured reservoirs, we tend to have matrix blocks that are of the order of a meter. The gravitational pressure drop that will drive flow, delta rho GH, right? Well, H is about 1 meter, G is about 10, delta rho is about 300 kilograms per cubic meter. So we're looking about a few kilopascals. On the other hand, we've got here a driving force due to capillary pressure. And often we're looking at relatively tight rocks, rocks with permeabilities of a few millidarcies. There, the capillary pressures are typically tens or thousands of kilopascals. So the order of magnitude of the driving force, the capillary pressure, is much greater. Okay, so therefore, we're going, for the sake of argument, we're actually going to ignore the gravitational term as well. So we're just left with this term here. Now we're going to write it in a more convenient form. And the more convenient form is as follows. We've got here a ds dt term. So we can write dsw by dt equals. There's a d by dx. But notice there's another d by dx term here. Okay, so they're going to be 2 d by dx. So we're going to write this as d of sw dsw by dx. And this is going to be, in fact, a key equation. In fact, it's the equation we're going to solve. Okay. So that's the equation. Now you might say, well, that's fine. But what's d? Okay, so we need to write down d. So d, right down here, okay, is the terms we haven't got. Now let's have a look at this. Okay, so we've got a d by dx of q. Q has got a k. Right, so we've got a k. Lambda W, lambda T, sorry, lambda W, lambda oil over lambda T. There's a phi term that we put over here, so there's a porosity term. And then here it's a ds dx, so we've got a dpc by ds. dpc by dsw. And the last thing, and it's not confusing, but if we look at this carefully, sorry, we need to actually see that bottom of the board. If we look at this carefully, we actually need a minus sign here because we put this over the other side, okay? Whereas here, there's a plus up here. So the minus sign looks weird. Ooh, the minus sign, that doesn't look nice. The minus sign is okay, don't worry about it. The reason why it's okay is, let's think about these terms. dpc by ds, remember our capillary pressure? I don't want to draw it out nicely, but saturation increases in this direction, capillary pressure goes down. So dpc by ds always has a negative, it's always negative, okay? So dpc by ds is negative, so this is our equation. Now, this equation sort of looks okay, but what can we do with it? Well, this equation is a non-linear diffusion equation. Okay, we got a d by dt is a d by dx of d, which is a dispersion or diffusion coefficient, ds dx. So for those of you familiar with this sort of problem, it's a diffusion problem. Now, don't overdo it with the mathematics. Really, it looks confusing. It's a little bit different from real diffusion. No, it's not real diffusion. It's how water or a wetting phase will imbibe into a porous medium. But this is the key point. How does a diffusive process propagate as opposed to an advective process? So when before we've looked at Buckley-Leverett, okay, which is an advective process. We inject water to displace oil. How far does the water move is governed by the Darcy velocity, and it goes linearly with time. It has a speed. You know, if it's gone so far in 1 year, it goes twice as far the next year. It's going with the flow. Distance scales with time. Don't think about all the other complexities. That's all. If it's a diffusive process, and it's diffusive because here we have a second spatial derivative, diffusive processes go, x goes as the square root of time. And this we're going to show. I'm going to show mathematically, but you need to understand it physically. Any random or diffusive process, or in this case, process described by this type of equation, x goes as root t. It doesn't go linearly with time. It actually goes as the square root of time. So the time taken to go a certain distance scales as the square of that distance. That's the key point. If you've got that point in your head, then the maths follows. If you haven't, then it's always going to be a bit of a muddle. So let's, now what we're going to do is we'll just go through then a transformation of variables. So how do we deal with that particular problem is as follows. So I'm going to get rid of the material we don't need. Actually, for the moment, I don't need D. Okay, I don't need this. I'm going to use this equation though. Right. So what I'm going to do now is I'm going to define new variables, and I'm going to see if we can find a solution that's just a function of these variables. And the variable is omega, or W if you prefer, is x over root t. And just as I did in the Buckley-Leverett solution, I looked for a solution that was a function just of v, x over t. Here, because it's diffusive, right, it's going to be x over root t. Don't panic. If it doesn't work, it doesn't work. Let's see if it works, okay? So now we've got a d by dt and a d by dx. So a ds by dt is equal to dsw by d omega, right? d omega by dt, which we can work out. We just differentiate it is minus x over root t times t. So this is equal to minus omega over t. Okay, when we differentiate it, dsw by d omega. Then we've got a 2d by dx terms. Okay, so we've got to get rid of those. So a d whatever by dx is 1 over root t. Okay, because it's just d by dx, we just get 1 over root t, d by d omega. Now, when we put it in the equation here, let's think about it. We've got the d by dt, so it's minus omega over t ds dw. Here we got a d by dx and another d by dx. That's a d by dx at constant time. So there's one root t here and another root t, and they can come out of the equation. And also, if you're spotting this, I've made a mistake. When I differentiate, there has to be a 2 here because it's 1 over root t. Okay, so I had to divide by 2 because it's the square root, more minus, right? Minus omega over 2t. Okay. So let's substitute that in the equation, and I'm going to write it down here. So we've got here minus omega over 2t dsw by d omega equals. Then we got 2 of these, so we've got 1 over t d by d omega of d dsw by d omega. Okay, now the beauty of that is, yeah, it is going to work because the t's cancel. Okay, so I can get rid of the t's there. I've got a minus, I've got a 2. Let's not panic about that. Okay, so let's get rid of the t. Okay, like that. Okay, so how are we gonna deal with this equation? Okay. Looks a bit tricky. So at this point, okay, we have a nonlinear equation. We've done our change of variables, but we seem a bit stuck. And actually, at this point, most people were stuck, okay, with this equation. It's a nonlinear diffusion equation. You do these variables, but you're still left with something complex. The main, well, I would say, insight to allow this problem to be solved came originally from Sunadra and Werter and was picked up in the petroleum literature by Schmidt and Geiger. The idea here is to use an analogy with Buckley-Leverett. You know, we look a bit stuck here mathematically, and in fact, we're going to end up with something that looks a bit weird. But the key insight is this. In Buckley-Leverett, we have this variable v, x over t, but we also know that v, the velocity, is df ds, right, where f is the fractional flow. So what I'm going to do is just I'm going to assume, and don't worry about this, in a partial differential equation, if I make an assumption and it doesn't work out, I made a mistake. If it works out, it's fine, okay? So what I'm going to do is I'm going to assume that there is a fractional flow, okay, f, such that the solution is omega is df by ds. Now, at this point, well, what's if? Is it the fractional flow? No, it's not the fractional flow because qt equals 0. You're going to get yourself in trouble. So what we're going to do is we're going to find the fractional flow. And this is where it's different from Buckley-Leverett. I can't just say this is the fractional flow equation. I'm going to find the fractional flow. And once I have it, then I can find x over root t, and the solutions are just a function of x over root t, just as in Buckley-Leverett, they're a function of velocity. That's the idea, okay? So what I'm going to do now, right, and it enables me to solve this equation, or at least simplify it. Okay, so how do I do it? What I'm going to do is I'm going to do an integration first, because if I notice this, if I put the dw over here, and dw over here, quotes, it cancels. But what I want to do is I want to integrate this. Okay. Well, this is the integral of d. Okay, so this just becomes the thing itself. So this is just d dsw by d omega. Okay, so that was easy. And this now becomes minus omega over 2, sorry, minus a half the integral of omega dsw. Sorry, I haven't written the omega formula. Okay. So, okay, well, that's fine. But now, here's the key. Look at this. If I look at this, omega dsw is just df. So this is just df. So the integral of df is f. So here, this is just minus f over 2. Now, that hasn't given me anything because, what is it? Now I've got this dsw by d omega term, so how do I deal with that? And also, shouldn't I have a constant of integration? Well, the constant of integration, that's not a problem. Let's look at this fractional flow f. What I'm going to define f as follows. I'm going to define f so that, like any fractional flow, at the initial conditions, it's 0. The water isn't moving. And then at the maximum saturation, my S star, I'll just call it F star. Okay, so this is the maximum value. This is the minimum value. So in this constant of integration, right, if I integrate this, you can have f, but then there may be constant of integration. It's okay, because we know at the initial conditions, f is 0. The capillary diffusion coefficient, which has a water mobility in it, that's also 0. So when d is 0, f is 0. So it turns out there isn't an integration constant. And if you're sort of worried about this, you can look at it in a bit more detail. It is okay. But I still need to deal with this dsw by ds by d omega term. So let's get rid of, this is standard stuff here, so I can get rid of that. Let's have a look at this. Well, let's just differentiate this again. D omega by dsw is d2 f by dsw squared, which I can call, if I want to, just f double primed. Okay, it's second derivative. What's this? dsw by d omega, is it flipped? So actually, this can be written as, right, equals just d over f double prime. Okay. So now we can rearrange this. It all looks a bit, what's going on? We started with this equation, and we end up with, we got f double primed is minus 2d. So let's write that out. And that is the main result. Okay, now, why is this such a result? You know, so I'm not really getting it. Yes, look at it carefully. F is something we need to find. Okay, once we find it, we have the solution. I'm going to show schematically some solutions in a bit, so don't worry about it. Okay, D we know it's this complex function of saturation, but it is a known function of saturation if we know the fluid flow properties. Okay, formally, this can be solved. We know the boundary conditions. We know that at the initial conditions, this is 0. We know there's some maximum flux. So how might we solve it? The way in which you can solve it formally is as follows, and you have to use an iterative process. That f, right, can be written as a double integral. You've got minus 2d over f, and then a double integral, because then f double primed is minus 2d over f. Now, this looks a bit weird. You can, in fact, simplify it. You can change it into a single integral with integration by parts. I'm not going to say much more about this, but you have to solve this iteratively. You have to guess a function f, and normally just a linear function. Okay, so something is just linearly proportional to saturation. Put it in this integral, integrate it, find a new value of f, and put it back. And as I said, I'm not going to dwell on this in a great deal of detail. It's actually quite straightforward to do. A few iterations, and you get this function of saturation to arbitrary accuracy. So while it's not really an analytic solution, I can't sort of write down f equals function, which I then differentiate. You can, in fact, find the fractional flow and, in consequence, a solution to arbitrary accuracy. Okay, so it's a semi-analytic solution. And the point here is that this is an equation for f in saturation space, not in terms of distance and time. And that's why it can be so accurate. You're just actually finding it's a function of saturation, just like Buckley-Leverett. So if you're interested in the details in chapter 9 of my book, you can find more mathematical details and more examples of this process. That's as much of the maths I'm going to say. And I just want to introduce one other idea, and then I'm going to show some example solutions. The first is, well, this f, what does it really mean physically? Okay. Well, the way in which you can think about it is as follows, is what is the water flow? Q, we know this, Q is equal to, because we wrote it down to begin with, was K lambda W lambda oil over lambda T dpc by ds dsw by dx. Okay, and just for reference, right, d, our d function was minus k over phi lambda w lambda oil over lambda t dpc by dsw. So it was basically almost the same terms. Okay, so we can write q in terms of d. Okay, so it's equal to minus, because there's a minus sign, there's a phi here, minus phi d. Okay, then ds dx, right, can be written as ds d omega over root t. We just rub that out, but it's relatively straightforward. So there's a root t, and this is dsw by d omega. And if you remember, that was, do you remember omega was df ds, so d omega by ds was d2f, f double primed, and this is 1 over f double primed. So that's 1 over f double primed. So we can get rid of this, and that's f double primed. And then let's look here, d over f double primed is minus f over 2. So we get this as phi f over 2 root t. So the way in which you can think of f, this fractional flow, is it's actually just the water flow as a function of saturation. So the water is imbibing rapidly at the inlet, so that's its maximum flow. And then as the water moves in, the water saturation is decreasing, and so the water flow is less and the oil flow is less. And eventually, when you're away from the imbibition front, there's nothing going on, right? The water flow is 0 because F is at the connate water saturation. So F actually is just a rescaling of the water flow. You get this 1 over root T because imbibition is a 1 over root T behavior. The rate of imbibition scales as 1 over root T. It starts off super fast and it decays with time. It's not when I pump, when I have a constant rate, okay? So I have a variable rate that goes as 1 over root T. The other interesting thing is, I don't know this a priori until I solve this equation, and this equation has to be solved iteratively, right? The way I've shown it is, you put in a guess and see if it works, and that's correct. If I've got my, trusty piece of rock, there it is, and I want to know how fast it imbibes, I know all the fluid properties, but the imbibition rate is a result of those properties, and mathematically they emerge from it. I have to solve iteratively. I have to find out what works. I can't just say the imbibition rate is X. Okay, so how much actually imbibes? We'll get rid of all of this. How much imbibes? Well, that's the total amount imbibed. So I can define QW is equal to the integral of Q dt, naught and T, but this is the total amount that imbibes at the inlet. So this is QW star, where we have F star here. And now the integration, and I'll try and remember the factor of 2 because that comes out, okay, is just phi F star times root T. So the total amount that imbibes goes as root T. Eventually you're going to reach the end of the system and the imbibition stops. That's outside this analysis, okay? But during this time, it's just proportional to F star. So basically F star, which is the maximum imbibition rate, is solved iteratively from knowing all the fluid properties and actually gives you this rate of imbibition. And this is why this semi-analytic solution works much better than just solving the original equations, because you have to discretize in space and time and you don't know the imbibition rate. You put the wrong amount of water in your first grid block numerically, and then the whole solution is incorrect. This gets it very accurately. So the final thing I want to do is just show some example solutions, and I'm only going to show 1 or 2. And I'm going to leave up D here. So what does the solution look like? Well, the solution is going to be, right, saturation on this axis against, well, if it's Buckley Leverett, it will be V, X over T. Here it's just X over root T. And for any given time, that's just the saturation profile as a function of distance. Again, it's exactly the same, it's just root T, not T. Okay? In 0 to 0, this is my connate water saturation, which we have initially. This is my, say, SW star, my maximum. So what does the solution look like? And it all depends on this D. At the connate water saturation, D is 0. Why? I've already said this, because the water mobility here is 0. That means the diffusion coefficient tends to 0. There's no diffusion, there's no spreading. This D, the diffusion or dispersion coefficient, is how things spread. Nothing spreads, then it's a sharp change in saturation. So you can, again, prove this, but at the leading edge, it's not quite a shock, but you have an infinite gradient. Then what you tend to find is if you have a strongly water wet case, so let's do strongly water wet in blue, at SW star, you want minus SOR. So actually D is also 0 here because the oil doesn't move. So it's sharp here. So if it's strongly water wet, you get this. Right? So this is your water wet. Now, what about an oil wet rock? Just a minute. Oil wet rocks repel water. There's no imbibition at all. Nothing happens. SW star is SWC. There is no spontaneous imbibition. Okay, what happens if it's mixed wet? Well, mixed wet rock is obviously going to have SW star is lower because it doesn't spontaneously imbibe so much. And a mixed wet rock, this is what's interesting. You don't imbibe all the way to the residual saturation. So D is finite at SW star. So it doesn't go down vertically, right? It has a finite slope. Still not there. But what does it look like? The fascinating thing is, and this is in my other lectures, in a mixed wet rock, initially, the water relative permeability is very low at intermediate saturation. So lambda W, just in case you're worrying about it, yes, it's the relative permeability divided by the viscosity. Okay, and this would be of water in this case. The relative permeability is really, 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 really low, which means D is really low. So there's very little driving force, very little capillary dispersion. So in a mixed wet rock, this can have a shape that makes sense, but is much, 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 much slower. So you can have imbibition times that aren't, slightly slower, 30% or something. Ooh, that looks big. No, not even 10 times slower, but thousands of times slower. Okay, and it's because the water mobility is so low. So this was a typical mixed. Okay, so this is just a very brief schematic of what the solutions look like. As I said, there are other solutions available that I published and other people have published. This is just a brief overview. But the real things to take away is physically, what is spontaneous imbibition? Soaking into a piece of rock, soaking into a tissue. There's a mathematical theory for this, very elegant one-dimensional theory. It describes the process with this semi-analytic solution, which looks a bit weird. FF double prime is minus 2D. It is weird. I'm sure you haven't met something like it anywhere else, but it is able to be solved relatively straightforwardly with arbitrary accuracy. And then we can get these analytic solutions. And these analytic solutions gives us insight into the imbibition process, but they can in theory be used if you could measure the saturation profile in an experiment. That will give you D. And from the D, you'll be able to back out your fluid properties. Okay, well, I'll end there. Thank you very much.